Welcome to video 1 in this course ST3 on probability. Here we're going to talk about terminology and concepts. Please see video 0 for parsing the logistics and video 2 for a short video on the Monty Hall problem. So here we're talking about basic definitions of statistical features, things like random trials, which is an experiment with at least two possible outcomes whose occurrence can't be predicted with any specific certainty. An example of that is flipping a coin, rolling a dice, or considering when will the bus actually come. An event is related to this because that's the subset of possible outcomes of a random trial. It could be a single item within that subset, or it could be a collection of them. It depends on what we're trying to describe. And that comes from a sample space S, typically. So S contains a bunch of different events, and we're looking at differing probabilities of different things. And S is generated by a random trial. So therefore, we can apply this and think about the events that might occur, such as rolling a heads, getting a number 6 when we roll a 6 per dice. And when will the bus come? Yes, it will come, but it'll be out of service. We can represent probability in different ways, and a good way of representing this is a tree diagram that's also called a probability tree. So this represents the branches of different outcomes in multiple random trials used to determine probabilities. So say we take a binomial probability of the two different options. We roll the dice. So we roll the coin, flip a coin here, might have outcomes of heads or tails, and we can repeat this here at this point and repeat tossing the coin. You might get heads again, or equally you might get tails. Both outcomes are possible. On this kind of tree diagram, this gives us a representation of the different outcomes that could occur. We might think we've got heads and heads. We might get heads and tails. We've got tails and heads. We might get tails and tails. So these kind of diagrams kind of give us a way of graphically representing the different options. And here, each of these has a probability of a quarter. And we can work that out by multiplying the probability of each step, where each of these have an outcome of a half and a half. And therefore, we can multiply the half by the half to get a quarter. So that's where tree diagrams can be more useful, and you can think of more elaborate ones that give us this series of outcomes, even though they may repeat like this at this second stage with multiple different outcomes that repeat. So an example of what that would be that you have two balls in a box, you close your eyes, you grab one, and you know the color and place this, and that's where you might get red or blue here. And you can repeat this process many times with replacement, obviously. We also have to define what we mean by probability. So that's probability of a particular event. It could be a single item, but it refers to the number of times of A occurring if we run the experiment over and over again. And a corollary of this is that all predictions are based on sampling. So we should also report such information with measures of uncertainty. So it's not so much the certainty that we're trying to grapple with, it's estimating the uncertainty of our measurements. So when we describe these probabilities, we can refer to probability event A, B, C, and so on. And what's important to note is that they must all sum to 1. So often that can be useful in describing things. We might have two probability of events, probability of heads, probability of tails, and it's convenient to note that the probability of tails is equal to 1 minus the probability of heads if we've got two different outcomes. Sometimes this is also denoted as probability of A prime or probability of A with a C at the end, the complement. If A and B are mutually exclusive, they're sometimes referred to as disjoint. And what we can say there is that the probability of A or B is equal to the probability of A plus the probability of B. So the probability of A and B is therefore equal to 0. So this means that A and B are completely independent. And that's often important for your biological data sets because that can be a key assumption for testing different processes. If A and B are not independent, that can mean the probability of A and B is equal to the product of these two events occurring. And this will be non-zero. So if we have the probability of A or B, we get the probability of both minus the probability of this occurring. And graphically, you can imagine that there you have probability of A or B occurring. We're measuring probability of A here, this circle, and B here, this circle, which means we have duplicated the intervening purple area. and that's why we need to take it away at the end. So these sets as a Venn diagram are a way, just like probability trees or graphs, are also a good way of representing events that might occur in a particular sample space. So if B has already happened, we can denote A given B. So this horizontal line, vertical line, indicates A given B. So that means B has already happened, and therefore asking what's the chance of A. So if the probability of A and the probability of B are entirely separate, it makes no difference, and then this is equal to the probability of A alone. But if they're overlapping, like this, then the probability of B having already occurred may affect the probability of A, and this calculation becomes more complex, so we use Bayesian logic then to determine what that is. So an example of this would be that you take 10 samples, which 2 will be chosen, and number 5 is already taken. And that means if you're looking at the probability, say, of choosing a particular number like 7, instead of being a probability of 1 in 10, if 5 is already chosen, that must change to 1 in 5, because the number of options now has changed. What we can also say is that the probability of A and B is equal to the probability of A multiplied by the probability of B given A. So this kind of symmetry means that we can kind of think more carefully about these probabilities and look at Bayes rules later. And that is written as the probability of B given A is the probability of A given B multiplied by the probability of B divided by the probability of A. And you can remember this because B given A means that the B is the numerator and A is the denominator. And then we switch this term at the front. So that Bayes rule will mean that we can estimate different models based on these calculations. So we can think about different rules that occur. So we had that multiplication rule already, referring to the probability of A and B occurring if they're dependent on each other. And we also have this corollary that if they're independent, then this is simply the probability of A by the probability of B. If there's also the addition or additive rule, the probability of A or B is equal to this term that we mentioned already. And therefore, if they're mutually exclusive, the probability of A and B, like we had before, is equal to 0. So A and B are like this. What we can consider then, if we expand our coin tossing example to looking at a bunch of dice. So if we look at this example, where we're trying to predict rolling a 3, and we sum across the different options of rolling from a 1 to a 6 for B, and then we look at the probability of rolling a 3 given all these different options. So B takes on these values. So if we look at these are 2 dice for like A and B that are shown all the way through here for the 6 different options. If we're looking at the probability of rolling 3 for A here, we're looking at the options in this set. So what is graphically obvious when we enumerate the different options is that this is 1/6 of the total options, because we got 6 out of 36. But we can go through and think about how this works. So if we roll 2 dice, in this instance, we know that they're independent. So the probability of rolling, say, 3, given that we rolled a 2, is equal to 1/6. So therefore, if we're looking at the probability of A rolling a 3, we can sum across these different probabilities. So rolling a particular value like 1, and the probability of rolling a 3, given that we rolled a 1 already. And we do the same for 2, probability of 2, multiplied by the probability of 3, given we rolled a 2 already. So this is 1/6, but this is also 1/6 together. So that's 1 over 36 we get there, and we get the same here, 1 over 36. And therefore, when we add the 6 options together, probability of 6 by the probability of 3 given 6, that's going to be 1 over 36 as well. We'll sum that up and we'll get 1 out of 6 altogether. So consequently, when we're thinking about these different options, we can get the probability of A by looking at all the alternative options. There's summing the probabilities of A for all the potential options for B. So let's look at some examples of questions. Starting with one on very basic probability. So you can think about what the numbers of pigs with chronic ASFE, African swine fever virus, what is the probability of the pigs selected at random has been infected for under 4 months. So that's going to be the sum of these divided by the total here, which is going to be 50, I think. So that's going to be 27 over 50 for A. And then what if has been infected for at least 8 months? So that's going to be this set here. So that's going to be 8 out of 50 satisfy that criteria. Then we can look at other questions using sets. So this question, we're thinking about two events A and B. They're represented by a diagram. A and B, here, this middle portion is 0.1. A and B and A complement, so that's this area here, is 0.3. And that obviously means that the probability of B alone is a summation of those areas, so that's 0.4. Probability of A and B complement is X. That means the probability of A is equal to X plus 0.1. We're asking us probability of A in terms of X, and hence find the value for which the events A and B are independent. So that means the probability of A and B is equal to the probability of A by the probability of B, which is equal to 0.4 by X plus 0.1. So what we can do is therefore work this out, that the probability of A and B is already given here. It's given as 0.1. So therefore we just need to solve this equation. So what we would get there is 0.4 by X plus 0.04 is equal to 0.1. So we can work this out then, that X is going to be 0.15. So that corresponds to this area here. So that's where I think about independence is important, that if A and B were not independent here, that would be more complex to work this out. Another basic probability questions, we can think about having some sort of bag poorly drawn here like this. And we've got 6 red discs, numbered from 1 to 6. So we number them there. Five, 6, and then we've got 4 green discs. So I'll try to grab another color if I can. I get green. Number from 7 to 10. So 7, 8, 9, 10. So that's in our bag. And then we have a bunch of blue discs. Oh dear. We have a bunch of blue discs. So again, I'll try to switch my pen color to blue. And this is in A here. And then over here we have B with our container. And these are shown as 1 all the way to 10. So you can represent them like that. And they're in box B. 2 discs are drawn from box A and 2 drawn from box B. So we've got 2 here, 2 here. They're without replacement. What's the chance that the discs drawn are 2 red discs and 2 even colored blue discs? So that means we've got to look at the probability of getting red, and the probability of red again, given that we put true red already, multiplied by the probability of getting blue, and even multiplied by the probability of getting blue and even, given that we already do blue and even. That is spelled already. So we can think about this value. So probability of drawing red for the first time around is simply 6 over 10. Red, given that we already do red, there's only 5 reds left, and there's only 9 discs in here to draw from here. Probability of blue and even is just going to be a half here, because we've got half or even 5 out of 10. This time it's going to be 4 out of 9. That product will give us our answer. I'm not sure what it is, but you can work it out. We apply the same logic to the next portion of the question. We're asked, try 1 red disk, 1 green disk, and 2 blue disks with all 4 disks odd numbered. So this is more complex, whereas we're looking at probability of red plus odd, and half of the red are odd, so that's going to be 3 out of 10. The probability of green plus odd is the same logic, just 2 out of 10. The probability of blue plus odd works the same way as before. We got 5 out of 10. And then the same again, it's going to be 4 over 9. Similar question. What about a red disk on its own? That's going to be red, green disk, and then 2 blue disks. But here we're told that the red and green disk, they must sum to 10, and that the blue and disk must also sum to 10. So visually, this is more complex. This is more complex problem that can help if you visualize it. So if we look here, what we're thinking about is that these values, if we look at red plus green equals 10, we have green ranges from 7 up to 10, so 10 isn't possible. Red ranges from 1 to 6. 1 to 6 is what we have. So there's only certain combinations that actually work to give us this. So for example, 7 plus 3 for green and red will give us 10. Another one that can work is 8 plus 2. And then we also have 9 plus 1. So they all will satisfy that criteria. Same for blue and blue, which is more easy because you have more combinations that could work for that. And that could be, they could be drawn in either order if you think about it. So for example, blue and blue, that could be 4 plus 6. That could be 3 plus 7, 2 plus 8, 1 and 9. All satisfy that criteria. So what we can do is think about the probabilities as well, that the first item is going to have a probability of 1 in 10. The second is also going to have a probability of 1 in 9 as well. So for each of these, we have to choose the exact one to work out the values. So it's going to be a probability of 1 in 10 and 1 in 9 in each case. So if we choose 7 red at the start, we must get green 3. And if we choose blue 4, we must get blue 6. So in each case, we have a specific option for these different ones. So we can look at these graphically. So in this arrangement, I'll just discard them so you can get a better view. So we had this observation that it's going to be based on these probabilities of 1 in 10, 1 in 9, 1 in 10, and 1 in 9. And then we can enumerate the different options that are present to see what might work. So for our first instance, we got the blue disks here. And then on our other side, we have these are the red and green. So that's R and G. So for here, if we choose 1, then we have to get 9 to satisfy this. And same for 2 and 8. And same the other way around with 7 and 3, 8 and 10, 9 and 1. That's the same here, 9 and 1, except we have no option for blue here. So that means that the total we can take, that if we choose a particular color, it's going to be 8 and 9 multiplied by 1 and 10. And same on the other side, 6 and 9 multiplied by 1 and 10 as well. So these are the different options that are possible. So therefore, by taking the product of these, we can solve this question. In another question, we're looking at 3 cards drawn at random without replacement from Black 72. A more classic probability problem. Find the probability that 3 cards are the Jack of clubs, the Queen of clubs, and the King of clubs. That's looking at the exact set that we're getting here. Jack of clubs is going to be 1 over 52 because there's 52 other cards, and this is the exact card. The Queen is going to be 1 out of 51 because there's only 51 left. And then same way, it's 1 out of 50 for the king of clubs, and we're multiplying these by each other to work it out. What's the chances that these cards are aces? So it's any ace. That's going to be 4 over 52 by 3 over 51 by 2. Oh dear, 2 over 50. You see that there. Another question, by the probability that 2 cards are black and 1 is a diamond. So we're looking at black, black, diamond. So we for each of these, it's essentially 1 1/4 at the start, because we got 13 out of 52. Then for the next step, we've got 12 out of 51. And then for the diamonds, we've got 13 out of 50 cards that are remaining. So that can give us our answer there. What I should have mentioned as well is that the sequence can vary. So we've got black, black, diamond, which I mentioned at the start. We've got diamond, black, diamond, black, and then diamond, black, black. So the 3 different options. You need to multiply this by 3 at the end. And then we're asked about what's the probability that the 3 colors are of the same color. So the colors are red and black. So we're asking what's the chance that all these are the same color. So that's the same for any particular ones. So if they're all black, 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 that'll be that particular set. So that's going to start off as 26 over 52 by 25 over 52 by 24 over 50 for that. And we just multiply that by 2 to get the probability for either black or red, red, red. So that can cover some basic questions on basic probability. What we can talk about next is permutations and combinations. So permutations are when we're selecting a particular number of events, k, from n in total, and that's in a particular specific order. So we sometimes denote this as npk to determine the n permutations from which we're selecting k options in particular order. And we can calculate the probability of that as n factorial by over n minus k factorial. So that's shown there. So that's on the numerator, it's n by n minus 1 by n minus 2, all the way down to 1 on top. And same for the denominator, n minus k minus 1, and so 1 is 1 down to 1. And that can be summarized as this as well, going from n all the way down to n minus k plus 1. So that's a kind of shorthand. An example of this would be, say we draw 3 cards from a pack in the orders king, queen, and jack. A permutation requires a particular order, so it's not king, queen, and jack in any order. That's a combination. So in this case, we'd be asking, there's an example of this in bacterial genetics where we're looking at gene names. They have exactly 4 letters. So how many possible names could therefore exist? So for each letter, we're assuming that it doesn't make a difference if it's the previous letter, so we could have a name that is A, like that. So that means we were just looking at 26 factorial by 26 factorial by 26 factorial by 26 factorial, because there are 26 options for each step. And if we're using RStudio, we can write this as using the factorial function. So factorial 26 gives us that value. Another example is how many can exist if each letter per name is unique. So that means we can only have one A, B, C, D, etc. like that. Each letter has to be unique within the name. That means we have 26 options at the start, then 25 options, then 24, then 23, and we can write about that in R in the same way. Related to permutations are combinations. So here we're selecting k events again, but that's in any particular order. It's not a specific order. So you might have n choose k such that n choose k is n factorial over k factorial by n minus k factorial. So this is the denominator. The factorials work out in the same way, and you might have this sometimes written as n choose k, so n choose r, or nr in these round brackets. So for example, if we have a 4-digit lock with numbers 1, 0 to 9 for each particular locking point, we therefore would have 1,000 different combinations to look through. We can write this as a binomial coefficient as well and use this function choose in order to calculate these ones. For example, if we have choose 10, 4, we have 240 options. And note that OR assumes no replacement, but you can toggle that when you're running using this code. So if we have an example of this is the birthday problem. So if we have n people present on this course that are online in person, what is the chance that any two of us share a birthday? So we know the probability of having a birthday for the first person is going to be 1, because they must have some birthday. And then if we're looking for the second person, we're looking at this probability that the second person shares that particular day. And at the start, that's going to be 1 over 365, which is kind of easy to calculate. As it becomes more, as we add more people, it becomes more tricky. And therefore, what you can think about is the number of people that are present. So the probability of them sharing a birthday at the start is simply going to be 1 minus 364 over 365 at the start. And we use the same logic then to expand that to more people. So if we have more people, we can use this formula. That's 1 minus n choose k as the numerator divided by n to the power of k as the denominator. So therefore, we can say that if we have 1 minus if we're looking at k data options, so let's say we have 6 people or 5 data options, we have 6 to the power of 5 as our denominator, and therefore we can work out using this formula that we can do 1 minus 365 all the way to 360 by 365 to the power of 6. And that might give us 4% if we have n equals 6. And then if we increase that, we might find that it becomes larger. We can expand these binomial problems to multinomial ones as well. So if we think about many different classes, so say if we're rolling a dice, we'll have numbers 1, 2, 3, 4, 5, 6. The sum of the probabilities of the different options will sum to 1, and we might have multiple classes of outcomes. And we can use the same approach for calculating that. An example would be we might have 56 playing cards, and therefore what we can do is take n factorial as the numerator and then work out for the different classes at the bottom as the denominator. So you may use multinomial models in your work, but they're just an extension of the binomial one that we're going to concentrate on more later. So final question in this area, we'll be looking at for example, strings of letters, just like our bacterial names, and how many might we have in the name repetitive. So here we've got, if we count the letters, we have 10 letters. So if we have 10 unique letters, it would be 10 factorial, but it's not. We got 3 repeats of E en route, a bit like if we were looking at assembling DNA sequences. We got 2 I's, and then we got 2 T's as well. R, P, and B are unique. So here in this particular question, because we're asking about how many distinguishable strings can be made from this, the order of the I's, E's, and T's don't matter. So for E, we got 3 factorial ways of arranging that. For I, we got 2 factorial, and therefore for T, we have the same 3 factorial as well. So therefore, they can act as a denominator for our different options. We have 10 factorial at the start. We've divided by these numerators because they're restricting our different options, in which case we get this number of 50,000. So hopefully you've got a feel for basic probability calculations, the basic aspects of probability that we can apply further later on in this course.